Hola, bonjour, konnichiwa. Okay, so the next section is on the gas laws. There are going to be 3 gas laws that we're going to look at individually, and then we're going to put them all together into one nice, neat formula. So I am going to do individual videos for each of the 3 gas laws, and then finally the combined gas law, and give you lots of practice on each. They're super simple, straightforward formulas, just like in physics. So we're not actually doing conversions, although converting might be involved. But we'll see how it goes. So scientists have been studying physical properties of gases for hundreds of years. In 1662, Robert Boyle discovered that gas pressure and volume are related mathematically. The observations of Boyle and others led to the development of the gas laws. The gas laws are simple mathematical relationships between the volume, temperature, pressure, and amount of gas. Anyhow. All right, so the first video is on Boyle's Law. Boyle relates pressure and volume, and I'm hoping that possibly you might be able to actually use your ThinkMeet to figure this out. So what happens to pressure? So you're going to, what do you call that? You're going to manipulate one of the variables and you're going to look at how that affects the other variable. And so for Boyle's law, it's pressure and volume. So let's say I have a 1 liter container that contains 1 mole of gas. Now, what is going to happen to the pressure if I cut that volume in half? So I have 500 mils, but I still have 1 mole of gas. Do you think pressure is going to go up? Do you think pressure is going to go down? Or do you think the pressure will not be affected? So that's Boyle's law. Like I said, I'm hoping that you can kind of figure it out based on being that you're all so clever. So Boyle's law states that the volume of a fixed mass of gas varies inversely with the pressure at constant temperature. So there's going to be, for now, there's going to be 3 variables that we're going to be comparing. We're going to be looking at pressure, volume, and temperature. Now, if we're comparing volume and pressure, that means that temperature is being held constant. Excuse me. If we're going to look at pressure and temperature, then we're going to say volume stays constant. And if we look at volume and temperature, that means we're keeping pressure constant. So those keep those 3 things in mind as we go through these. And I have a nice little trick to show you, like a visualization that will help you at the end of this, but we're going to look at each individual law first. So the volume varies inversely with pressure at constant temperature. So Boyle's law can be used to compare changing conditions for a gas. We use P1 and V1 to represent the initial conditions, and P2 and V2 to represent the new conditions based on the following equations. So the first thing that I want to do actually before I do all of that, to show you how we go from, wait a minute, just wait a minute. Okay. So I'll have to switch to another color. Unfortunately, the Keynote app doesn't give me an option to erase, so I can't do anything about the stuff on the screen. Anyway, I want to go based on the definition. The volume varies inversely with pressure. So volume is proportional to the inverse of pressure. Okay? Now, if we want to change the proportionality, which is that squiggly line, we want to change that to an equality because we can't do anything mathematical with the proportion to. So if I want to change the proportion to an equality, I have to introduce k, small k, meaning a constant. So I can say V equals a constant over P. And then just to make everything nice and easy, I'm going to move this to the other side. So let me go down to the bottom right, and PV equals K. All right, I want to show you how you go from the definition of volume is proportional to the inverse of pressure. Inverse of pressure means 1 over P. I'm going to change proportionality to equality by introducing K, constant, and then I'm going to put all the variables on one side, because now I'm going to introduce my P1 V1 and P2 V2. So P1 V1 equals K and P2 V2 equals K. So I can put them together and say P1 V1 equals P2 V2. And that is how we can use the formula for Boyles law to calculate. This is a graph that shows you what an inverse proportion looks like. So at low pressure, we have high volume, and at high pressure, we have low volume. They're inverse, okay? If you have a direct proportion, the graph would look like this. Okay, so sometimes on entrance exams or SATs or things like that, they ask you to identify what a direct proportion and inverse proportion looks like. Direct proportion is a straight line going up, and inverse is that curve going down. So let's practice. A sample of oxygen gas has a volume of 150 ml when its pressure is 947. The big clue, not clue, but the big chore, I guess, for you guys is to be able to identify correctly what P1V1 and P2V2 are and which one you're supposed to solve for. So a sample of oxygen gas has a volume of 150 ml and a pressure of 0.947 atm. What will the volume of the gas be? So that's V2. You're solving for V2. At a pressure of 0.987 atm if the pressure remains constant. So you are given V1 is 150. You're given P1 is 0.947. You're given P2, which is 0.987, and you have to solve for V2. Now, as long as your volumes are in the same unit, and your pressures are in the same unit, you don't have to convert anything. But if I give you liters and milliliters, you pick one of those two to convert so that both of your volume units are the same. And again, both of your pressure units are the same. You don't have to convert anything unless I ask you specifically for a particular unit in the answer to the question, which I might do. And then you can't forget that 1 ATM is equal to 760 millimeters of mercury, 760 torr, and 101 kPa. Those are the four main units that are used. Okay, so that's all of our given information and our unknown. So we're going to rearrange Boyles law, which is P1V1 equals P2V2, and we're going to solve for V2. So we're going to take P2 and move it under P1V1. So we get V2 equals P1V1 over P2. We're just going to plug in our numbers. Please, please, please be careful when you're plugging in your numbers. Make sure that you have the correct number assigned to the correct variable. Excuse me, I need to eat breakfast. The biggest problem that I see in students doing these types of questions is not that they don't understand how to do it, because it's really should be really straightforward, but it's in making a mistake and accidentally swapping out P1 for P2, something like that. So just make sure that you do everything very, very carefully. Okay, so then you get a volume of 144 milliliters. And remember, we to cut our units. All right, so let's do a couple of practice problems. A balloon filled with helium gas has a volume of 500 ml at a pressure of 1 atm. The balloon is released and reaches an altitude of 6.5 kilometers where the pressure is 0.5 atm. Assuming that the temperature has remained the same, what volume does the gas occupy at this height? Now, in grade 10, I told you how to solve chemistry problems as you always look at the number and unit that you're given in the question, and you identify all of the information, the data that you are given. In this particular example, this 0.65 K is extraneous. It doesn't mean anything. You don't need to use it. So I've got P1 V1 equals P2 V2. And which of these variables am I given? I'm given V1, I'm given P1, and I'm given P2. So I have to solve for V2. And again, I rearrange my equation. Maybe you're like super confident. You're like, nah, I'm just gonna like plug it in there and do it all myself. But I like to rearrange so that my unknown variable is by itself on one side. So I've got V2 equals, and I take the P2, put it under P1 V1 over P2. So I'll just put that on the other side. P1 is 1 ATM. V1 is 500 ml. And I'm going to be really and absolutely demand that every single number has a unit in your solution. I don't want to see 1 times 500 over 0.5. I want to see all of the units because I want to make sure that you remember how to cancel or cut your units. So I want to see all the units. So ATM's cut, I'm left with ML, which is a volume. So that makes sense. So V2 is equal to 500 divided by half is 1,000. Where's my calculator? Nope, don't have my calculator out. Hold on. Where did it go? Calculator, there it is. Okay, so let me go back here. I'll drag that up. There we go. So I've got 1 times 500 divided by 0.5. Yeah, 1,000. 1,000 ml. Okay. And underneath all the scribbling, yeah, you can see that it's 1,000. 1,000. Another example. A gas has a pressure of 1.26 ATM and occupies a volume of 7.40 liters. If the gas is compressed to a volume of 2.93 liters, what will its pressure be, assuming constant temperature? Okay, so I've got P1 is 1.26 ATM, V1, 7.40 liters, and V2 is 2.93 liters, and I'm gonna solve for P2. So P1 V1 equals P2 V2. I solve for P2, so that's P1 V1 over V2. Okay. But P1 is 1.26 ATM. V1, 7.40 liters. V2, 2.93 3 liters. Let me get my calculator again. 1.26 times 7.4 divided by 2.93, and that's 3.18. Oops, not liters, because I'm solving for pressure, ATM. And that would have helped if I would have followed my own rules and cut my units. Anyway, 3.18 ATM. Now, the last thing that I want you to do is see if your answer makes sense by applying the concept of Boyles Law to your answer, and that is that it's inverse. So what I mean is, what's happening to volume? V1 is 7.4, V2 is 2.9. So volume is decreasing. What should we expect the pressure to do if volume decreases? Based on Boyles Law, they have an inverse proportion. So if volume decreases, pressure should go up. We started with 1.26. We should have a higher number than that, and we do. So yay, it makes sense. 3.18. Okay, I'm gonna leave this one for you to try. Or should I? Yeah, I am. Okay, so your assignment. And this should be interesting because I'm not gonna say anything except for here in the video. So I will know who watched the entire video by knowing who actually turns in this assignment. Your assignment is to do this question. I want to see your solution. Divers know that the pressure exerted by the water increases about 100 kPa with every 10.2 meters of depth. This means that at 10.2 meters below the surface, the pressure is 201 kPa. At 20.4 meters, the pressure is 301 kPa, and so forth. Given that the volume of a balloon is 3.5 liters at STP, remember what STP is, and that the temperature of the water remains the same, what is the volume 51 meters below the water's surface? So your only assignment for today is to solve this question. And I want to see that uploaded to GC on this assignment. Good luck.